The topic today is going to be mass spec mixture quantitation of labeled compounds, presented by myself. My name is Don Keel. I'm a PhD analytical chemist who's worked at Cerno Bioscience, a company that specializes in mass spec calibration software since 2004. And I'd like to give special thanks today for our collaborators in the data that we're going to be presenting from Xenobiotic Labs. This is a outline of the presentation that we're going to go through today. Excuse me, I don't know why. I'm getting some technical problems here. This is an outline of the presentation. We're going to talk about, first of all, the calibration approach for mass spectrometry that makes this type of quantitation of isotopically labeled mixtures possible. And we're going to just review the importance of this peak-shaped calibration and what we call spectral accuracy, which is critical for the application of this technology. And we're going to talk a little bit about how we apply it to both unit resolution mass spectrometers, such as quadrupole instruments, as well as high resolution instruments such as TOF, Orbitrap, and even ICR instruments. And after that review, to give you a little background, we're going to go into our isotope mixture quantitation and discuss our approach to this. We'll overview very briefly some of the current approaches, and then we'll talk about our combination of our calibration approach with a least squares best fit approach using using our software. And then we'll conclude with a bit of a summary. Okay, to get started, this is an introduction to okay, I don't know what's going on here. I'm gonna excuse me, I'm having a little technical problem here. Let's try this again. Okay, hopefully everybody can see my screen. So we're going to talk about our mass spec calibration approach, and this is just a typical mass spectrum collected on a quadrupole after it's been processed to show the centroided data of a typical compound there. In reality, mass spec data is not collected as a series of centroided peak positions, but instead it's a continuum. And this is the raw data that you would typically see as is collected from a low resolution quadrupole instrument. In reality, the true mass spectrum is a series of, if we had infinite resolution, looks very much like that centroided data we saw. However, in reality, at the n+1 and n+2, etc. peaks, there's actually a number of adjacent closely spaced isotope peaks as well. And after we centroid data, this fine information will be lost. And of course, this information is key in that it really adds to the overall shape of that mass spec profile peak. And if we look at the low resolution data from mass spectrometer of different compounds that are at approximately the same mass position, that isotope information, as we all know, can be used to clearly differentiate between different compounds, even though the molecular weight of those compounds is pretty close. And so again, this is low resolution data, resolution of about 800. And again, the information of the isotopes underlying those peaks is what gives each spectrum a unique fingerprint. In a conventional mass spec calibration, we typically will calibrate the instrument for typically only the spectral position of the peak. The interesting thing about mass spec is that it's quite unique and that it has the ability to the mass spec can be calculated very precisely. It's one of the few analytical techniques where we can use first principles to calculate the spectroscopic data. In this particular example here, we're showing a theoretically generated mass spectrum, which is in blue here, and the measured mass spectrum. And if we do the calibration, what we'll typically do is we'll typically shift the peaks so that they align with the known mass, and we perform what is therefore known as a mass-only calibration. Our approach is quite different, and it's quite necessary if you're going to do quantitative deconvolution of overlapping peaks, which is what we're going to talk about today with our isotope analysis. It's very important that we do a proper full calibration, what we call our TrueCal calibration. So this is the measured mass spectrum. So effectively how our calibration works is we look at the monoisotopic peak and we estimate the width of that monoisotopic peak, and we choose a line shape which is mathematically defined, which we're going to be using as a calibration line shape. And this line shape is typically mathematically defined line shape, such as a Gaussian or a Lorentzian line shape peak. So from that peak, that's the peak that we're going to choose, okay, to represent our mass spec peak. And of course, we can now calculate exactly what the actual spectrum should look like from first principles. So here we have the mass positions of the isotopes and the different isotopes. What we then do with our theoretically or calculated mass spec is we simply convolve it, that line shape that we choose, with that calculated mass spec. So what we have here is effectively a perfect mass spec of at a defined resolution, which represents that underlying spectrum. Now what we can do in our calibration is we can simply look at the difference between the calculated ideal mass spectrum and the measured spectrum. And we can, by deconvolution, calculate a correction function, which looks something like this. It's a vector that expresses the difference between the uncalibrated line shape and the calibrated line shape using perfect line shapes. And not only will it correct for the peak position, but it'll also correct for the peak shape. And to correct our mass spec uncalibrated, we simply apply this function. That produces a fully calibrated mass spectrum, which is calibrated now not only in mass position, but it's also calibrated in line shape. And overlaid here, what we have is the blue line is the uncalibrated mass spectrum, and the red line is the calibrated mass spectrum. And the calibrated mass spectrum, very important, is calibrated not only in mass position, but is also calibrated now in line shape. And this is extremely important. First of all, what it allows us to do is, even for a low resolution mass spec, it allows us to now position and the monoisotopic peak to a very high degree of mass accuracy. Even though it's a relatively low resolution spectrum. That's because we know exactly what the mathematical line shape is, because we've defined it in our calibration. While in a typical vendor specification for such an instrument, you may have a specification for mass accuracy to about 0.2 to 0.5 Dalton. After this calibration, the mass accuracy is improved to about plus or minus 0.005 Dalton, or about 5 millidalton. And this is typical of all quadrupole instruments. And this is about 100 times better mass accuracy than is routinely obtained on a typical quadrupole instrument. Now, the other very important thing is, in addition to calibrating the mass position, we've also calibrated the line shape. So now what we can do is we can take a theoretical or calculated mass spectrum that's calculated using that same known line shape, and we can use it to compare to the measured mass spectrum. And you can see how good the overlay is. That enables us to do very accurate mathematical fitting to help us in not only mixture deconvolution, but also in formula identification. And we call this spectral accuracy. So there's two things that are very important for doing these isotope mixture analysis. One is, of course, the mass accuracy, and the other one is the spectral accuracy, because the spectral accuracy, or that fingerprint, is going to help us deconvolve complex mixtures. Now, for high-resolution data, we take a slightly different approach for calibration. High-resolution data already is typically calibrated because of the high resolution to very good mass accuracy. However, it's not calibrated to the line shape, or what we call the spectral accuracy. But what we can do in mass spec is we can take advantage of the fully resolved monoisotopic peak, which is isotopically pure. And we can use this as the calibration function for the rest of the isotope pattern in the mass spectrum. So again, we take a pretty similar approach. We use that isotopically pure line shape to generate our calibration function, which we then can apply to our high-resolution mass spec data. So in this case, we'll be calibrating the line shape to get good spectral accuracy, but we do not improve the mass accuracy, but it's not necessary in a lot of the applications that we're going to talk about. So what we have here then is now in red is the theoretical or the calculated mass spec overlaid with the calibrated, and just for reference, you can see the uncalibrated data, just to give you an idea how well we can actually fit with spectral accuracy. If you're interested, there's more information. There's back in 2010, there was a feature article in Analytical Chemistry that fully covers and describes how this particular calibration works. Okay, now let's move on into the application side of things. And like I said, today we're going to talk about isotope mixture quantitation. And what we're going to talk about today is we're going to just very briefly overview the importance of it, and talk a little bit about the current methods used for isotope mixture quantitation. Then we're going to talk about the approach that we use that combines our ability to calibrate the mass spec not only for mass accuracy, but for the spectral line shape using our TrueCal approach. And we're using a least squares fitting approach. This is a classic multivariant fit of multiple spectrum to deconvolve a highly overlapping mass spec. Without that calibration, however, this multivariant approach is difficult, if not impossible to do. And then we'll do a quick summary, and then I'll open things up for questions at the end. Just a brief overview. Certainly isotope labeling is used in a lot more than metabolism studies. It's also used in forensic work as well as environmental work. It's commonly used as an internal standard for LC-MS quantitation. C13 labeling is used for as an internal standard for metabolic flux analysis, and of course, labeling with hot compounds such as tritium and C14 as a radioactive tracer is very important in ADME studies, mass balance studies, and can also be used to accurately do quantitation. However, the big challenge here is that, of course, these isotopes are very difficult to differentiate. Certainly chromatography, difficult if not impossible in a lot of cases to do separations. So we have to resort to other methods. And just some of the common methods, obviously for the radio-labeled compounds, we can use a radioactivity detector, very sensitive, highly selective. It does require special care, lab certification, and a special detector. And it's a bit tedious and time consuming, but is a well-proven technique commonly used for radio-labeled compounds. NMR is obviously a very good approach for analyzing these mixtures. The downside to NMR, of course, is the sample volume that you need, the sensitivity issue. Mass spec is also used as a very good tool and has been used in the past, and there's a number of published studies there. It's universal, can look at both hot and cold isotopes. You can do deconvolution to some level of accuracy, but usually not to the level of accuracy that's required for many experiments. Typical published literature values for the accuracy of deconvolving these isotope mixtures is in the range of about 20 to 10%. Anything lower than that, and the approaches typically tend to fall apart. And this is just shows you a series of a compound which is labeled with a single C13 stable isotope, two C13s, three C14s, so on and so forth down the line here. And what we're trying to illustrate here is that, of course, the spectrum shifts, but what happens is you get significant overlap, obviously, with the M+1, with the M+2 peak, so on and so forth. So even with a high resolution, this is a zoom in of the C13 peak, even at high resolution, we can't resolve the C13 peak, okay, from its natural abundance. So it gets very hard to distinguish these mixtures. So the approach that we've taken is a little different from what's been expressed in the literature. In the literature, there's approaches typically involve subtraction out of a background, and then successive subtraction or various types of modeling. We've taken an approach which is a multivariant approach, and simply what we're doing is since we've calibrated the mass spec using our line shape and spectral accuracy calibration, what we can do is we can calculate the isotope patterns of the compounds of interest, and we can very precisely fit them to the measured calibrated spectrum. And we can use a simple linear least squares fit. This is no different from the equations that you would be using to do the least squares best fit of a number of points to a straight line, except now we're just working with vectors instead of single values. So it's really quite a straightforward approach. So the first thing we tried with our partners is we tried the experiment using a high resolution mass spectrometer, which happened to be a LTQ Orbitrap instrument. And what we did is we used the calibration approach that we discussed to calibrate our line shape, which is shown here in red. That's the actual measured line shape, and we calibrated that to our known line shape function so that we could fit the isotope patterns using that regression approach. So this is the raw spectrum from the Orbitrap, and what's now overlaid in black is the calibrated data. So we've calibrated the high-resolution spectrum to a known line shape, and that means that we can now fit theoretically calculated spectrum, including isotope spectrum, very precisely. And here we have a very good fit, which you can see the spectral accuracy here is at about 90.6%. That's quite a good fit. As it turns out, with the Orbitrap as well as other trap type instruments, one has to be careful because we have ion-ion effects. Ions that are closely spaced in mass can interact with each other, and they can distort the spectrum. And this is also known as the space charge effect. And as it turned out, and this is a paper that was published back in 2009, that if you want the best spectral accuracy, there is an optimum resolving power that you need to set the Orbitrap to. And the reason for this is because in an Orbitrap, the higher the resolution that we measure at, the longer the time the ions spend in the trap. And this gives the ions more time to interact to provide nonlinear distortions to the spectrum, which limit our ability to provide good spectral accuracy. So the first thing we tried with our partners is a simple experiment. We had a compound that only contained carbon, hydrogen, nitrogen, oxygen, and fluorine, and we did a C14 label, 50-50 mixture. We did our calibration, and what happens in the software is the software, you can tell it which isotopes that you want it to fit. It'll automatically calculate those spectra, do the least squares fit, and produce the mixture results, which are shown up here on the left in yellow. And it turns out the mixture wasn't pure. The compound wasn't pure. It was a 50-50 mixture. So if you take into account, these mixture results are actually quite accurate. It's very, very good results. The other verification that we have is that if we then calculate theoretically what the specific activity of the labeled compound is, we come up with about 29.2 millicuries per millimole versus the actual measured, which is about 28.5. So we're in good agreement there. So that gives us a high degree of confidence that our fitting is working quite well. The next thing we looked at was a chlorine-containing compound. And this is where things start to get interesting. Of course, with chlorine, we have a large natural abundance at M+2 of chlorine-37. What does that mean? That means at M+2, we have a high concentration of ions, okay, that are closely spaced in mass. So that gives more opportunity for the space charge effect to have an impact on the spectrum. And interestingly enough, you'll see that the spectral accuracy here for the calculated to the measured calibrated spectrum is now reduced to about 97.3%. So we suspected what was going on here is we were having an ion-ion interaction at M+2, which was giving us a problem with our spectral accuracy, which of course would affect our ability to provide accurate quantitation of our isotope labeled compounds. The next step that we did is we took that compound and we labeled it with 2 deuteriums. And what happens, of course, is now we have another ion that's closely spaced in mass, the D2, along with the chlorine. And again, we have a opportunity to have space charge effect come into play. And indeed, what's happening here is we have a further reduction of our spectral accuracy. And finally, we took a 50-50 mix of the cold to the labeled chlorine-containing compound, which provides even more opportunity for space charge effects at N+2 and N+4 now, and indeed our spectral accuracy is degraded even more. So it's interesting because spectral accuracy is now kind of a problem indicator. It helps us indicate that there's potentially a problem with our spectrum. And if we looked at the mixture results from this particular compound, we'll see that they're quite far off. It's a 50-50 mixture, and the mixture results from the fitting, our linear least squares fitting, is problematic. If you look at the blow up of one of the isotope peaks over here to the right, you'll see that the theoretically or the calculated spectrum and the calibrated measured spectrum are quite different. So indeed, something is going on here, and primarily what we think the problem is a space charge effect. So one has to be very careful when doing this kind of experiment with trap type instruments. To validate this further, what we did is we actually took the same mixture and we measured it in simple single quad instruments. Now, quadrupole instruments have very little, if any, issues with space charge effect, because basically the ions are dispersed over a very broad space. So if we take the measurement and we do the calibration as described previously, and we look at the mixture calculated overlaid with the measured calibrated, we get a very good agreement of about 98.7% spectral accuracy. And again, our mixture, 50-50 mixture results, they're a little off, but that's only because the labeled mixture was impure. If you take that into account, we get an almost perfect result of 50-50 mixture. So indeed, we can get very good results for doing isotope quantitation, but we need to be careful about the nonlinearities in different types of instruments. Okay, to really test this approach, what we did with our collaborators is we purchased commercially a labeled compound, C14 labeled compound, where the benzene ring here could be labeled at any point with a C14. And in fact, it could be labeled not at all. It could be labeled in 1, 2, 3, 4, all the way up to all positions. So it's actually a mixture of 7 possible isotopes, including the native species, and then single labeled C14 through C16. So we designed an experiment where we produced mixtures of the hot provided compound, which could be labeled again anywhere on that ring, with the native unlabeled, and we wanted to be able to evaluate our ability to predict the mixture components using this particular compound. And again, the instrument that we used was happened to be a Waters triple quad instrument running obviously MSMS, and the manufacturer provided us with the specific activity data of 62.7 millimoles per millicurie for this particular compound. Okay, so we actually did 5 repeat measurements for all of these mixtures in order to evaluate statistically how well we could perform this quantitative work on isotopes. And what I have here pictured at the top here is the 100% cold labeled compound. So what you see here in red is the calibrated data. Okay, and then overlaid with black, that's the theoretically calculated data. So we have a very, very good fit here. And below is the 100% hot, 100% pure hot, which was again C14 labeled. And from this, we know that the compound as provided, not all of the compound was C14 labeled. There's some percentage of it that was not labeled. Of course, the manufacturer cannot provide us with this data, but we could calculate this based upon our fitting, and we calculated that the compound as provided by the vendor was 66.8% labeled, and the remaining were unlabeled, or was the unlabeled compound. Just to give you an idea of really what's going on mathematically underneath, it's actually very simple. What we see here is a set of overlaid spectra. Again, these are calculated spectra. Remember, we can match very accurately our calculated spectra to our calibrated spectra, because we've calibrated the spectra both in mass position and in as well as in line shape. So effectively, what we have here is the calibrated mass spectrum in red here, okay, and underlying it is the data that has been fit. And of course, the amount of each vector that gets fit to this spectrum to match it best as a least squares fit can be quantitated. So that enables us to do full quantitation of effectively a 7-component mixture. And the bar graph here is on the left side just shows you the relative amounts of each labeled compound, which would be no carbon labeling, all the way up to 6 labels on that particular compound. This is just to give you a feel for what's going on underneath. And of course, this would be difficult, or if not impossible, to do without calibrated line shape. This is some of the results that we came up with this particular experiment. Up on the upper left-hand corner here, this is the cold compound, and this bar graph just shows the fractional concentration of each isotope. And of course, since it's 100% cold, you would expect effectively no labeled C14, and you can see effectively it's very close to 0. There's also standard deviation error bars here, since we did the measurement in five separate times, and you can barely see those in here. This is on the lower left. This is a 50-50 mixture of the hot and the labeled. So what this is showing is that using our mass spec deconvolution approach compared to the volumetric calculation of the isotope distribution, we have very good agreement, okay? And this is, again, for a 7-component mixture, all right? Again, in the upper right, this is the 100% hot mixture. We get, again, not only do we get good agreement with the volumetric data, but if we calculate the specific activity based upon the distribution of these isotopes, we get a value of 60.6 millicuries per millimole, which compares excellent with the actual vendor-provided specific activity of 62.7. And the fitting accuracy here for this data is on the order of almost 99%, which again is excellent. Finally, on the lower right plot here is we basically have a plot which should be linear, okay, if the fitting is good, which plots the calculated percent cold with the predicted percent cold, okay. And you can see that we have a very nice correlation of over 0.99. But more importantly, if we look at what we call the SEC, or the standard error of calibration, which is basically the total error in predicting the known from the measured data, we have an error of about 1.8%. This can be compared to previous techniques with much fewer compounds, which start to fall apart down at levels of about 10 to 20%. So a vast improvement in our ability to quantitate complex mixtures. And again, it's important to note that since it's a mass spec technique, we can do this with both hot and cold labeling. Okay, let's finally just, we're going to do a little summary here, and then I'll open things up for questions. First of all, the mass spec quantitation of overlapping multiple species is quite feasible, accurate, universal, sensitive, and convenient. It's very straightforward and easy to do with this technique. One of the very nice things about this technique is that the unlabeled compound is actually used as the calibration compound. So it makes the experiment very straightforward to do. Of course, without our ability to calibrate for spectral accuracy, this would not be possible. The spectral accuracy not only provides the ability to get good quantitative results, but if you have a problem, either with the mass spectrometry itself or perhaps with the chemistry, the spectral accuracy values are a great way to diagnose problems and to raise questions about poor results. So if the spectral accuracy is poor, that indicates something's the matter with the measurement. So it's a great flag to diagnose your problems. Third, this approach is actually quite viable with unit resolution quadrupole mass systems. It's quite easy to do. It could be even used in for walk-up evaluation of these labeled compounds. Again, it's dependable and robust because of these diagnostics. Clearly, high resolution data is always better, especially with complex mixtures. However, the word of caution there is it requires special attention to the problem of mass accuracy. We've got to be very careful about nonlinearities in the measured spectral data. And of course, other applications, some of which we'll explore in future seminars, which will also be published works, is in mixture identification quantitation, deamidization, deamination, hydrogen deuterium exchange mass spec experiments, metallo-organic chemistry, as well as environmental and forensic problems as well. And of course, there's always the application to GCMS, where we can solve the problem of de-resolving the components of the of the molecular ion peak with the molecular ion minus proton, which is always a challenge in EI mode. Okay, with that, if you want to forward your questions to our host, I'll be happy to answer any questions.